Hi, I'm Vladislav, and my topic today is color in scientific graphics. And I will make a small introduction to some theory about the color, but also we will go to illusions, and finally we'll go to color blindness. Most importantly, I will show you some solutions. Easy to implement, very easy to implement. So about the color systems, now let's guess whether you know this guy or not. Who can guess first? Who is this one? Isaac Newton. So he was one of those scientists who is very famous for some things in mathematics and physics, but he was also developing the color theory. Um, Usually, the scheme that's shown here is called a circle, and it's not in his Optics, this very famous book. It's not colored. Perhaps he was colorblind as well. There are rumors about this. And who is this one? Don't read. Helmholtz, he introduced triangle. And this guy, he is actually here standing. But you might guess who that could be. Maxwell. That is the first colored picture, photograph. He just, he put colors together to colorize the photograph. This famous, also Nobel Prize laureate, he's, uh, he's actually from Estonia as well, as me. Wilhelm Ostwald. And finally, very famous, very important for our field. Schrödinger, exactly. So he's actually developed the math for what we know today, this kind of thing. I forgot how is it called, but this contains everything what we know about color. And usually when you see something in your scientific graphics, we're actually using one of the models, like a triangle here. Or you see RGB or CMYK or Adobe RGB. It's just part of the whole color space. And you can present it in many ways, like this, triangle, or you can just make a circle, or you definitely have seen these triangles like this. But in 2022, saying that no, Euclidean space doesn't work, Riemannian space doesn't work, and what we perceive as color is more complex. It doesn't mean anything for us. We will still do at very low level of understanding the color. But for your screens and for TV screens especially, that makes a lot difference because we need shortest distances between colors. So there is a lot of progress in that field, and it's still open question with a huge market. That's all about here. Let's go further. Can I? Okay. Now we start with this cycle, and we don't want to have it as a spectrum. We would like to say that there are some colors we can distinguish. We are actually limited in how many colors people can remember and tell out loud. So very briefly, there are three primary colors. There are three secondary colors in between. If you take two colors, three colors, four colors, which are very close to each other, we call them analogs. If they are opposite, they are complementary. If you say you take some rectangular shape, then you will have kind of square with four colors. And for us, it will be pleasing to see four colors like this. They are apart and they are distinguishable on the circle. And you can do the same trick with a split complementary kind of triangles like this. Then you have shade, tint, and hue. Whether you understand it or not, you're actually using this because many times you will do this trick. You have some kind of trend and you would like to show it with maybe transparency, maybe hue, tint, or shade, or something like that, or maybe with a color. And even more, you can, for example, here is animal A, B, C. You would like to emphasize something with a color, like here. And in the B plot, you emphasize that these two are kind of similar animals, maybe chimpanzee and orangutan, but this one is a wolf, so we will use another color. Or here, you just say, this is not important, take a look here, with a color. So you can play a lot, and you do it already. Now let's go through visual illusion. I don't want to spend much time on that. If you haven't heard about it, you can go to Google. But could you please count how many colors we see here? And show with your hands how many colors you can see. 1, 2, 3. Let's count white as also as a color. Okay. So this is still red. This is red. It's optical illusion. And this is the same red. But you see it differently. Grayscale, you know this. You should print out in a grayscale and see whether the graphics is still understandable or not. And this is why, because on this rainbow kind of map, the colors would look differently, but if you print them in grayscale, they are actually quite similar. Like this cyan and this yellow, they are pretty the same. What about cultural aspects? For example, you would like to stress something that there is a good catalyst. Let's make it green. Maybe that's a bad idea because actually, if you think about happiness or good luck, yes, in some cultures it is good, but in other cultures, I don't know why Eastern European it's actually wrong. I'm from Eastern Europe, still green, but maybe in China. So, Je, could you confirm that red is, the color of success, but green is not? And the same, let's take a look on well, heat is actually something that you might think that, oh, okay, in all the cultures, something is warm, then it's red. And if something is cold, then it's blue. No. My colleague made a picture, it was opposite, and I was asking, why is it so? That's because her father is astrophysics, and it's opposite in astrophysics. Actually, it is a black body radiation. If the temperature is higher, it will be more bluish, and the temperature is lower, it will be reddish. And the same with green is good, but not in all cultures. Pink for girls, blue for boys, but not through the history. Who is this guy? Dalton, one of the first scientists who claimed that he has some deficiencies. And one of 12 men has some blindness. Women are okay. Why is it important? It's because normal vision is 92%, and all others have some kind of deficiencies. Well, most frequent are okayish. They will see almost the same, but there is about 1% who will see very differently. Is it a problem or not? Let's see. That's what we can find in the literature. You can see that this is normal vision, and you can probably distinguish everything. So it looks fine. This is also some kind of color palette with 5 colors, and you can kind of distinguish. You can use some other color universal design. So let's compare. If we now put the same picture, how color deficient person see it, no way to distinguish, difficult to distinguish, much better. Absolutely no way to distinguish, a bit better. Okay, so at least you can distinguish. But probably this is not the best way to plot your data. So how about our work? My idea is, yeah, it looks great, but you cannot distinguish these colors, and also it's difficult to distinguish what is what here. What I would like to say here is that definitely it is obvious we've spent, like all of us spent a lot of time on doing such graphics, awesome graphics. So if you just apply one fix for this about 1% of people who do not distinguish colors, that would be even more awesome, right? So there might be a problem. So let me just write the numbers from left to right on the board, and if you don't see the same, just let me know. So if you see the same, it's okay. No? What's wrong? 42? Okay. And you can take the test as well here. Actually, I saw one picture on Wikipedia that suggests I'm a bit colorblind, but all other tests I can pass. So, solutions. There are first, zero solution. The first to consider, grayscale. let's go. It's very good article here, and if you go through that scheme, that we start with some graph we have, then first just check how does it look in grayscale, then consider lines, line types, line width and brightness, then go to maybe you put some points, maybe you would like to have direct labels instead of legend, or maybe you have the same but a bit more advanced, and then you go what if you use one color just for one line? Maybe you split something, or finally you will get something like this, which is better than what we have here at the beginning. Or you can go and add more colors like this. So this is a pretty easy scheme. If you can, just use grayscale. That is first advice that you can find in the literature. The second will be decision tree. So this is about choosing the continuous set of colors. And I'm not going to go through all of this. The main thing is that you can end up with a conclusion whether to use this kind of map, this kind of, or this kind. And where you can see these maps, you can go to matplotlib, and they have a lot of maps like this. And they are quite different, so if you go to the link and see what's the difference between them, then you will understand what you need. But there is a way to do it systematically, scientifically, showing in the literature with all the references. What I would like to highlight that probably you just need 4 or 5 colors for your plots, right? And in that case, there are Seaborg and Matplotlib. And what you do here, you just create your own color palette by saying that I would like to use this color blind, which is here, you can see, and you would like to use 6 colors for your plot. Or the same with Distinctify. You also would like to have 6 colors. This is more advanced because you can also change the pastel factor, which I like. And finally, in Matplotlib, there is also table AU, colorblind 10. The limitation is that usually you have 10 colors only. How does it look like? You can immediately see those Gaussians here. So I really suggest you try it for those who are plotting Gaussians every day. And you can do it kind of manually by using common sets. There are 2 references here, one and another one, with a huge theory of how they derived the sets, and they have 12 color, 8, 15, 24, infinite number of colors. But they provide all these numbers here so that you can take them and put into your code. For example, this is my palette for 10 colors, and that is so easy. That's how you define your colors. Okay? And finally, you can make your palette. I think that Amanda, you also have some websites, so maybe you can send me a link later. But very good is Color Brewer 2, and also from Adobe, they have a new feature. You can go to color accessibility. That is very fun to use. What about your figures? If you would like to check how do they look like, you can go do it online, or you can again install this Distinctp with a pipe, and you can use it. If you use GIMP, there are filters. If you use Inkscape, there is also a filter to color blindness. And then you will change how it looks like. You can do the same for grayscale. So it's pretty easy. Who is using Inkscape here? Who is using GIMP? All right. And who is using Python? Good. And please don't forget to cite the code. So we're using Matplotlib. Have you ever cited Matplotlib? Please do. And probably Seaborg as well, and many all other softwares. Why not to acknowledge them? And that's it. Can you see what is written? And I guess that those directors and actors, they can agree, and those scientists as well, because most probably those were color blind, and these are definitely color vision deficient. And that's it. So today I'm going